for posterity, I'm gonna, and maybe each group can just share. Maybe each group can just share what they're at. So group 1. Oh, by the way, that was just over the course of the one-on-ones when I was sharing people like where the one-on-ones exist and where you can find them in Canvas. People realized that when I upload the pictures of the rooms, there are no names on the boards. And people said it would be nice if people remarked it would be nice if people started to put the name of their names on the board so that people know who wrote what, so that it's easier to like look through the boards and figure out where your work is versus somebody else's work. So just a thought. Okay, so group 1 or group 2, Chris, Ruby, and Lucian.
We chose the first question, throw a tennis ball straight up in the air. The ball reaches its maximum height, and the shape is the same, or the ball is the system, and the shape for both start and end is the same. We thought that the temperature are both positive for both the start and the end, and the speed would be 0 at the start and 0 at the maximum height or at the end. Yeah.
Cool. Okay, so anybody from that group wants to add anything to this? Okay, let's go to room 2. I think more than one people. So Ella, Ramsey, and Marin.
For this one, we did the one about the Hot Wheels car going left and right. And in this schema, the system was the track, the Hot Wheels, and then Earth's gravitational force. So that's like in the yellow.
So we didn't think that the system shape was changing because the car is moving horizontally, which means that it's not changing its distance between Earth and itself. It's just moving forward in one direction. And but if it was moving up, then it would be changing. So we just thought it would stay unchanged.
Okay.
And then for the system temperature, we said that it got large. It got larger by the end because the like friction on the car made it like larger. And then the speed, we said that at the start, like the car was moving 1.25 meters per second because like that's the speed that it says like in the problem. And at the end it's 0 meters per second because it comes to a stop, so it's not moving.
Cool. Yeah, that's great. Okay, let's do room 3. What do you guys have to, or room 4? Ella, Hillary, Isabel, and Keon.
I'll explain our schemas. So we had 2 schemas because we had one for before the ball had left the person's hand or before it was in the air. And we had one at like the moment it finished, I think. So our first schema is, our first schema is connected to less, and it's just because the tennis ball is interacting with less things. And also because gravity isn't, I don't believe gravity is interacting with the air. Excuse me. A tennis ball, Oh, they're actually pretty similar, but we had 2 different schemas. Yeah.
Okay.
And then for the system shape, we also said it was unchanged because it like stays the same.
Okay.
And the system temperature is also unchanged because we don't really know that it wouldn't necessarily be hotter, very minutely maybe, but it's quite negligible.
Got it.
And the system speed is 0 for both the start and the end because at the start, the moment the tennis ball leaves the hand, it's not moving because it's right after it leaves your hand. In the end process, it's right as it hits the ground, so it stops moving.
Got it. Can I ask a silly question? If it has a 0 speed, how is it leaving your hand?
Well, I guess it does have some kind of speed. Yeah, because you're dropping it, so.
Is it the moment? Is this experiment about dropping the ball, or is it you're throwing the ball up to a high height?
Oh, sorry, I meant throwing. I'm not sure actually.
Group, what do you think?
Well, the system speed, it's not 0. I mean, so we'd probably just have to measure it. We can probably do that through
I mean, you'd
linear analysis.
have to figure it out, but it's not 0, right? So,
Yeah.
in fact, and we know that the moment the ball leaves, not only is it not 0, but that's the biggest velocity it's going to have.
Yeah.
Because every time after that, it's going to slow down as it goes up, right? But I agree with you. So, okay, let's move on to the next rooms, and then we'll come back. Like, if there's stuff to talk about, we'll come back. So, room 1, Juliet, Hayden, Danielle. And then, so let's see. So you are also doing the Hot Wheel.
We are. And so yeah, our schema includes the air, the floor, the track, the gravitational force, and of course the car. The red circle is marking our system. Yeah, we chose to include the floor because though it's not directly interacting with the car, it's still supporting the track, which is interacting with the car. So technically, we might say that it is an essential part of the surroundings of the Hot Wheels car.
Okay, that's fair.
And then for our temperature, we decided it was just a positive number at the start. And then at the end, it would be a larger number just due to friction. And the speed at the start is 1.25 meters per second. And then at the end, it would be 0 because it's not moving.
And then for the shape, we said that the shape changes because the object, which is the Hot Wheels car, moves. So the large circle is the floor, the flat line is the ramp, and then the smaller circle is the car. So we said that for the shape for the start, the car is at the beginning before it moves, and then at the end, the shape has changed because the car moved.
Okay, cool. Again, we'll come back. We'll finish the last room, and then we'll come back to all the rooms to clean up a little bit. Okay, and last one, Lowell, Elliott, Hayden, and Natalia.
Yeah, so we also did the tennis ball demo. For our schema, we had the ball, like air molecules, the hand that's in the beginning, and the Earth's gravitational field. And so for the table, for the shape, we said it was unchanged because the tennis ball shape doesn't change if you just throw it up. For temperature, we said process start, it was a positive value, and then process end, it was also a positive value. And then for the speed, we said maximum speed because once it leaves your hand, it's gonna slow down because of like gravity. And process end, when it reaches its maximum height, we thought the speed would be 0.
Got it. For that group, when you say the temperature is positive and then the temperature is positive, it will be, from now on, it's going to be really important for us to distinguish. I agree with you, it's going to be positive. The question is one greater than the other? And which one is it, if there is one that's greater than the other?
Oh, wait, can I answer that?
Yeah, of course.
The process end, the process start is greater than the process end.
Why?
I think. Because I think the higher it gets up, it would get slightly colder, I think.
Because like cold air, like you.
Well, cold air, and also wouldn't it I guess I know, but when it hits the ground, it gets hotter. So I was just thinking like,
Totally, but and this again, like this is so you're right, Elliot. When it hits the ground, it's going to get hotter, right? So this is where we are going to need to be really careful. One, to read the information that's given, and two, to be very careful about defining the process, the start and the end. Because as Elliot said, when the ball hits the ground, it's going to get hotter. But look at your process. Does this ball ever hit the ground on the movie? And the answer is it doesn't, right? Because it leaves your hand and then it goes up to this highest height, and that's when you stop the movie. So it may very well hit the ground, or somebody might catch it at the top or whatever, right? But we don't know that because we, Lowell.
I agree with Elliot. Like, I think the ball will be colder when it reaches the maximum height. But I think that's true because, like, I'm pretty sure when objects move like faster, the molecules in them like move faster as well, which like causes the object to be like warmer. And when it's like at a speed of 0, I think like the molecules inside it would be moving slower. So the ball itself would be slow or colder.
Okay. Natalia, Natalia, I haven't heard you on this one.
Well, I think, okay. Well, I think, yeah, for the end, it's going to be cooler because I guess something that I learned in like 8th grade that I'm surprised I still remember is like convection currents. So like warm air rises and then it cools off and then it condenses and goes down. So I think it would be cooler at the end.
So you think it's going to be cooler at the end because of convection currents. Lowell says it's going to be hotter at the end because of friction.
Oh, and then like also at the beginning, not only do you have like the temperature of the ball, but you also have like the warmth of your hand. So I guess that could also make the start warmer than the end.
Yeah, Elliot?
also, isn't it that when molecules are like pulled apart, that's what makes something like get colder? Like the farther the molecules are.
That is
apart.
also true. If you take a gas and you extend it, you lower its temperature. All of that is true. For this particular experiment though, right? And again, like you could almost argue any way you want in this experiment, depending on what kind of factor you include in your experiment. Things to think about is when the ball goes up, it drags against the air. That causes friction. Friction causes temperature to go up, right? I agree with you, Natalia, that when convection current happens, when you go up, it cools and then it goes back down. I'm not sure what we're looking at as a convection current. So, right, like you're right, Elliot, that when you distend a gas, you lower its temperature, but there's no gas that we're distending here. So anyway, just a thought. But I love the fact that you said your system is unchanged, your system shape is unchanged because it's just the ball. So that was really, really cool. Temperature is either going to go up a little bit or just stay the same. Probably stay the same. Here, here's what I want to focus on. So I want to focus on the shape because the shape is going to be the hardest thing for us to talk about. So Dan said the shape of the system changed because, as you can see on the picture very clearly, there's the Earth, there's the track, there's the car, and the car is at a different place on the track, right? Question is, does that warrant us to say that the shape is different? And again, this is a really subtle point. This is not evident at all. Like, but you know, we're just like getting more and more familiar with how to work with this. So I'm going to redraw the drawing a little bit, and I'm going to draw it this way. So we are all on Earth. So I'm going to say there's a gravitational field, right? And then I'm going to say, here's my track. And I'm going to say, here's my car, right? And I'm going to make a movie of the car and the track on Earth, which is essentially like what this schema is saying, right? The car and a track on Earth. At the end, I'm still on Earth, so I'm still in the gravitational field. The track hasn't moved. My car is now on the other side of the track. And I'm going to make the same picture that captures the car on the track on Earth. And my question is, are those two pictures similar or different? Tate.
I do have a quick question though. Wouldn't the box that you're drawing encompass the entire track, not just the track on which the car rests?
Does it need to?
I mean, if that's supposed to represent our system and we are including the track in our system.
Totally. So Tate, I hear your question, right? And it's a really valid question, by the way. Why are we including the track? We're including the track because the Hot Wheel interacts with the track. So if I take a picture of the Hot Wheel interacting with the track, which is like below the Hot Wheel, that is the smallest picture I can take of that system. That still includes all the elements of the system, right? I have the car, the track that it's interacting with the car, and I am on Earth, so it's subjected to gravity. And at the end, I have the car, the piece of the track that the car is interacting with, and I'm still on Earth. And the question is, can I tell the difference between those two pictures? Ramsey.
I think that they're similar and basically the same.
Yeah. So, and it goes back to something that Ramsey, it goes back to something you said earlier in our conversation, which was, in order for the shape to change, what should be true about the track? Like if I wanted the shape of the system to change, what do I need to do to the track to make sure that that happens?
Curved.
Either make it, if I make it curved, what does that automatically do if I make it curved? What happens to the car on a track that's curved?
It speeds up.
It goes up and down, right? So if instead of this, I started drawing something like this, a track, right? I have the car up here. But now if I want to represent that the car is at the top of the track versus the next picture where the car is at the bottom of the track, basically the information I want to convey is how far away I'm from the Earth, right? From the center of the Earth. So then I need to take this picture to be able to compare them. I need to be able to take this picture from that picture. And those two pictures are different. So basically what I'm saying is, in terms of when you're dealing with the Earth, the only thing that we really want to know is, did your system go up or down? If your system goes up or down, that's going to have some massive implication for properties and energies and so forth. But if your system is horizontal, think of an experiment where like your track is flat for like miles and miles and miles. Do you care that you're on like this side of the track or that side of the track or that side of the track? If the mile is really like, if the track is really super long? So what I'm saying is, I agree with your drawing here. It looks like the shape has changed, but in fact, we don't really care about the shape, the change of the shape, because everything is horizontal and equidistant from the Earth. So that's something that moving forward, we just need to get, we need to get better at recognizing. Like that. Okay, let's see. I'm going to stop this annotation. Going back a little bit. There was one. Let's see, 3. So here, Ella, Hilary, Isabel, and Kian. Process starts, the tennis ball moves, and process ends when tennis ball reaches the highest height. And you say the system shape is unchanged. For which schema is this true? So first of all, in an experiment, you only do one schema for the experiment, right? Because the schema is sort of like, think of the schema as like all the actors in a movie. If you're watching a movie, you just have all the actors that are in the movie, right? You don't watch like that scene and then that scene and that scene, you watch the movie. So here you're saying, and you can decide to focus on the tennis ball and gravity, or you can decide to focus on the tennis ball by itself. But the schema is what it is, right? So you should choose one of the two schemas for your system schemas for your experiment. Once you've chosen one schema, which one of those two has a system shape unchanged? And which one has a system shape that does change?
I think the one on my right with only the ball circle would be unchanged, right? Because the one on the left, it implies when the system is both the ball and the gravity, then in relation to each other, when you throw up the ball ball is moving further away from the earth, or from I don't know how to explain it, but like okay. So it moves further away from the earth, and that would mean the system shape would be changed. But if it was just the ball, that means the system shape would be unchanged.
Awesome. Yeah, that's exactly right. Okay, and then 2, the track, the Hot Wheels, you said the system was unchanged. Temperature was larger, which I agree. The only reason the car stopped is because of friction, which meant that things would have had to got hotter at some point. And then the first one, so instead of saying system with an arrow, just make sure you put a circle around it, right? So we know which one you're looking at. But you're right, the temperature was unchanged. And again, you could say temperature, depending on whether you count air resistance or not. For the ball, it's probably not that important, okay? Any questions about any of the stuff that we just did here?